So we're in the middle of stating the second partials test, or the second derivative test for functions of two variables. So let me just remind you how far we had gotten. We've got z as a function of x and y. Okay. P naught is a critical point. F has continuous, whoops, I wrote first, I meant to say second. F has continuous second partials in some open disk containing that critical point. Okay, so if we have that, we define D to be this determinant. It's the determinant of the second partials, all four second partials of F, evaluated at my critical point. And we put the partials in these positions. F sub xx is here, then F sub xy, F sub yx, then F sub yy. That's important because this matrix whose derivative we're taking is actually the second derivative of F. Okay. Now, of course, when we take the determinant, it's this diagonal product, so it's the product of the two non-mixed second partials. And because we have this condition that the second partials have to be continuous, these two functions are continuous at and near P naught, so therefore they're equal. So we can say we're just subtracting that mixed second partial squared. Okay, so now I'm going to create a table here where I list the criterion that we have, and then how it allows us to classify our critical point. Okay. So we could have that D is positive. Now notice, the only way that D could be positive is if these two non-mixed second partials are the same sign. Now they could both be positive or they could both be negative, but in order for this thing to be positive, I need that first term to be positive, because I'm subtracting something squared from it. The smallest this thing could be is 0. If I subtract 0, I'm just going to get this product. This thing could be positive. In order for the difference to be positive, my first term would have to be positive and bigger than the term that I'm subtracting. So I would need that to be the case. So if D is positive, I know that my two non-mixed second partials have the same sign. That's kind of cool, because I understand what the non-mixed second partials are doing. They're actually giving me the second derivative of the cross-sectional curve in the planes I get by holding, in this case, y constant, and in this case, x constant. So that would say that those two cross-sectional curves had the same concavity. So if I'm looking in the plane where I hold y constant, so that would be a plane that's parallel to the xz plane, and I'm concave up, then I would also have that when I look in the plane I get by holding x constant, so that would be parallel to the yz plane, I would also be concave up. So I could have a situation like this that sort of suggests that I'm getting a min. If they're the same sign but they're both negative, both cross-sectional curves would be concave down, and that sort of suggests that I would have a max. So if D is positive, it's actually not enough to just know that D is positive. D being positive means that f sub xx and f sub yy are the same sign. So if D is bigger than 0 and f sub xx is also bigger than 0, then they're both the same sign. They're both concave up. That gives me that this is the location of a min. If D is positive and f sub xx is less than 0, and since they're the same sign, I just need to check the sign of one of them. And it doesn't matter whether I look at f sub xx or f sub yy. Usually we go in alphabetical order. We look at the first one. Okay. This would say that both cross-sectional curves are concave down. That's giving me a shape like this. That suggests that we would be at the location of a max. Cool. Okay. So I know if D is positive, I will have the location of a max or a min. But of course I want to take it one step further because I want to know which it is. To know which of those it is, I have to also look at the sign of the non-mixed partials. I'm going to continue this table over here. So I'll create another column for the criterion about D and the classification of my critical point P naught. Okay. So if D is positive, we've determined that we have a max or a min, and to see which one, we know we just look at the sign of the non-mixed partials. D could be negative. Now, there are several ways that we could make D negative. If these non-mixed partials have opposite signs, this term will be negative. I'm going to subtract something that's not negative from that, D will be negative. So that's one way that D could be negative. If one of these is 0, and this is not 0, then I'm going to have 0 minus something positive. That will give me something negative. Or I could have that these guys have the same sign, but this is just bigger. So that this is a positive number minus a positive number that's bigger, which gives me a negative. Okay. The scenario that's easiest to understand is when I know the signs of these guys. So I'm going to look at the situation where D is negative because these non-mixed second partials have opposite signs. Now, when that's the case, that would be telling us that one cross-sectional curve was concave up, and the cross-sectional curve in the other direction was concave down. In that case, I've got a min along this curve, but I've got a max along this other curve. When that happens, we've got a saddle. And that's what we call it. We say P naught is the location of a saddle. That just means it's a high point along some cross-sectional curves, a low point along others. Okay. The last possibility is that D could be 0. I'm not including D being undefined because we've stated that our criteria for using this test is that the second partials are continuous in some open disk containing our critical point. So if that condition wasn't satisfied, that would certainly mean that D was undefined. Well, wouldn't necessarily mean it was undefined if they existed but weren't continuous. But if this condition is satisfied, then D exists. Okay, so we don't even use the test if D doesn't exist. If D is 0, I don't know what happens. The test would be inconclusive. Okay. Now, that's not to say that we wouldn't be able to figure out that our critical point was the location of a max or a min or a saddle. We just wouldn't be able to figure it out by using this second partials test. Okay? So, if in the homework you're asked to classify the critical points, if possible, using the second derivative test, do that. Some of your results might be, for this critical point, the test is inconclusive. That's okay. Now, for individual functions, we might be able to figure out some other technique. Might involve looking at technology to try to figure out what's actually happening at that point. Okay. We're generally not going to be doing that. If you're asked just to do what you can with the second partials test, a perfectly acceptable answer is the second partials test is inconclusive for this particular point. Just make sure you demonstrate why that's the case. Evaluate D at that point and tell me that it's 0.